So uh, picture this. You move into a new house, right? You're unpacking boxes, and you find, I don't know, a single stray rubber band.
Oh, yeah. Always happens.
Right. And you obviously don't have a dedicated rubber band organizer yet, so you just toss it into an empty kitchen drawer. I mean, it makes perfect sense in the moment.
Completely logical.
But then, fast forward a year, you need a pair of scissors, so you open that same drawer, and it is just jammed shut.
Ah, the classic junk drawer.
Exactly. When you finally force it open, it's this chaotic wasteland of like dried up super glue, dead AA batteries, takeout menus from restaurants that closed 3 years ago, and tangled phone chargers.
Yeah, we all have one.
Right. But here's the thing. In the software engineering world, we actually have a name for that exact drawer. We call it the common library.
Oh, man. Or the core project.
Oh.
Or shared. Or utils.
Yes. Whatever name it hides behind, it's a trap.
It really is. It's a structural trap that, almost every development team falls into eventually.
Which perfectly sets up our mission for today. Okay, let's unpack this. We're looking at a super detailed technical article today about building a compiler-enforced modular monolith in .NET. And the author's main target is, well, that exact junk drawer.
Yeah, they point out that this shared library is it's a universal constant across our entire industry. Like whether you're writing C# or TypeScript, Python, Java, you will find this folder.
Oh, absolutely.
The author actually jokes that it's more dependable than a null reference exception with a call stack that, points everywhere except at the actual bug.
Huh. That joke lands perfectly because we have all been that developer just staring at that call stack.
Yep, completely lost.
So the goal of our deep dive today is to really figure out how to stop these shared libraries from mutating into these massive, unmaintainable monsters, and how a remarkably strict architectural approach can completely change how we organize our code and our teams.
I love that because if we look at the anatomy of this common library, this junk drawer, it doesn't start out malicious, right?
No, never. It's always innocent.
Right. You write a neat little string parsing helper method, and then another feature needs it, so you pull it into a shared space. Easy. But the author argues this inevitably creates two massive systemic pains.
Okay, let's get into those. What's the first one?
The first pain is cognitive overload. When you put a helper method in a shared library, suddenly every other project starts depending on it.
Makes sense.
But over time, that shared library needs to do slightly more complex things, right? So it starts depending on other parts of the system. And the dependency graph, which is supposed to be this clean, directional tree, just morphs into a tangled hairball.
Oh, I've seen those diagrams. They look like a bowl of spaghetti.
Exactly. You can no longer look at a piece of code and reason about a change in isolation because the whole concept of isolation has just been destroyed.
Wow.
Pulling one string tightens the entire knot.
Wow, yeah. And because it's woven into literally everything, that brings us to the second pain, right?
Yeah.
Which is the complete loss of ownership.
Right.
Because if the library is quote-unquote shared, the unspoken rule in, like, any corporate environment is that everyone technically owns it, which really means nobody owns it.
Precisely. Imagine a developer trying to make a simple update to, say, a date formatter in the Common project. They suddenly realize their change might ripple into the billing system, the user registration flow, and the notification service all at once.
That's terrifying.
It is. They don't have the context for all those domains, so they become terrified to touch it. The code basically ossifies. And the author uses this incredibly apt metaphor for this phenomenon. They call it the black hole.
The black hole, I like that.
Yeah, it has this immense gravitational pull. Code falls in, dependencies from all over your solution bend toward it, and nothing ever escapes.
Oh, and the most chaotic part is when that black hole starts spawning little satellite black holes.
Oh yeah, the spin-offs.
Right. The author describes the scenario, which is so real, where a developer is under a tight deadline, and they hit a circular dependency. The compiler just throws a massive wall of red text, because Common is trying to call into data access, but data access already relies on Common.
A classic architectural deadlock.
Totally. And in a perfect world, the developer would pause, trace the dependency chain, and, refactor the design to remove the cycle.
But in reality...
At 4 o'clock on a Friday, they just spin off a brand new project.
Yeah.
Now you have common.core and common.util.
And shared models.
Yes. You end up with this ridiculous constellation of ambiguous projects orbiting your solution. There's just no convention left. People drop new classes wherever the compiler allows it.
It really turns software development into an exercise in archaeology.
That is exactly what the author called it.
Yeah.
Archaeology, not architecture.
Right, you're digging through the code base, trying to figure out, like, why string extensions was placed in the core project, but bait extensions ended up over in Utils.
And then you run a get blame command to see who did this and why.
Let me guess, they already left.
Exactly. You discover the developer who made that frantic change during a 2019 refactor left the company 3 years ago. You aren't doing architecture anymore. You are just sifting through ruins.
It's so true. We have to ask ourselves, what were we originally trying to accomplish when we built these shared libraries?
Good question. What were we trying to do?
Well, the author suggests we're usually trying to implement a concept from domain-driven design, or DDD, called a shared kernel, but we completely abuse it.
Oh, so?
In pure domain-driven design, a shared kernel is a very small, highly deliberate subset of the domain model. It's something that multiple teams explicitly agree to share and maintain together.
The keywords there being small and deliberate.
Yes. But a typical common project is the exact opposite. We make a fundamental category error. We mix pure technical commonality like a method that capitalizes a string with domain sharedness, like an agreement on the business rules defining a customer entity. Mixing those two entirely different concepts into one bucket just accelerates the slide into a classic big ball of mud.
Okay, so before we look at the author's solution to the black hole, we should probably admit why the industry defaulted to our current habits in the first place. I mean, if you open a standard enterprise code base today, it is almost always organized by horizontal layers.
Right.
You have a data access layer, a business logic layer, an API layer, and maybe a models layer. We didn't do this just to be difficult, did we?
No, we did it out of a desire for separation of concerns. It was heavily influenced by the N-tier architectures of the early 2000s. There was this pervasive fear that one day the business would suddenly decide to swap out the entire underlying database system.
Right, moving from SQL Server to Oracle or something.
Exactly. So we built these massive horizontal layers to abstract the database away from the business rules.
But let's be real, businesses almost never swap out their entire database system on a whim. And in preparing for that incredibly rare event, we optimize for the wrong thing.
Quickly.
Think about the physical, visceral experience of navigating a layered code base in your IDE today. When your product manager asks you to fix a bug in the user registration flow, you can't just go to a user folder.
Oh, no. You have to open the models project to find the user Dido. Then you scroll down and expand the data project to find the user repository. Then you hunt through the services project for the user registration service.
It's exhausting.
A single business feature is smeared across 4 or 5 different projects.
And every time you expand and collapse those folders, you are context switching. You're trying to hold the mental map of the feature in your head while navigating a folder structure that literally doesn't care about features at all. It only cares about technical roles.
And because those layered projects are grouped by technical role rather than business purpose, they naturally degrade into catch-all dumping grounds. The services project becomes just, well, another variation of a junk drawer.
So what's the fix?
This is where the author proposes a major conceptual shift. We need to stop splitting our code by technical layer and start splitting it vertically by business feature.
Okay. Vertical slices.
Right. One folder per feature. Everything that feature needs, the data access, the logic, the models, lives together inside that boundary.
Which sounds great in theory, but slicing vertically immediately raises a massive structural question for me. If every feature has its own slice, how do we prevent them from tangling into each other?
That's the challenge, right?
Like, if the dashboard feature needs to show user data, how do they talk without creating the exact same hairball dependency graph we're trying to escape?
The author solves this by reaching for the Dependency Inversion Principle, which is the D in solid.
Here's where it gets really interesting.
It is. It's a principle we learn early on, but we often fail to apply it at the macro level. Dependency inversion dictates that high-level modules should not depend on low-level modules. Both should depend on abstractions.
Meaning interfaces.
Exactly. Rather than depending on concrete implementations, you depend on interfaces. And the author takes this standard object-oriented concept and applies it directly to the .NET project structure.
Let's trace the specific demo application the author built to prove this. The app has 3 business features: user, currency, and dashboard. Rather than putting all the user code into one user project, the author strictly splits the feature into two distinct projects.
Right, you get gav.user.contracts and gav.user.mpl, which stands for implementation.
Okay, so tell me about the contracts project.
The contracts project is the secret to making the boundaries work. It contains almost nothing. You will only find interfaces and data transfer objects DTOs inside of it.
No logic at all.
None. It has absolutely zero external dependencies, no database packages, no HTTP libraries. It acts purely as the public API of that feature. It's a lightweight promise of what the user feature can do without revealing anything about how it does it.
Okay, so if the contracts project just holds the promises, then the MPL project must be where the actual messy database calls and business logic live. The concrete class is doing the heavy lifting.
Exactly.
So if the dashboard feature needs to retrieve user data and then convert some currency to display on the screen, it will add a dependency to the user.contracts project and the currency.contracts project. It talks to the interfaces.
It communicates strictly through those thin, lightweight boundaries.
Wait, let me play devil's advocate here. If I'm a developer under a looming deadline working inside the dashboard implementation project, what is to stop me from just bypassing the interface?
The classic shortcut.
Right. If I know the user service class exists over in the user implementation project, it is very tempting to just add a direct reference to that project and instantiate the class myself to save time.
I love this question, because that temptation is exactly why mirror guidelines fail, and the author anticipates this. They utilize a specific visibility keyword in C# to completely neutralize that temptation. Internal sealed.
Internal sealed. Okay, what does that do?
When the author creates the concrete user service class inside the user.impl project, they do not mark the class as public. By marking it internal, they are telling the .NET framework that this class should be completely invisible outside of its own assembly.
Oh, wow. It's like a VIP room where the bouncer doesn't just block the door, they hide the entire room behind a false wall.
That is a perfect analogy. Even if a rogue developer wanted to bypass the interface, they couldn't. From the perspective of the dashboard project, the user service class literally does not exist.
The IDE won't even auto-complete it.
Exactly. The IDE won't auto-complete it. The compiler won't recognize it. The only way to interact with the user feature is through the public interface defined in the contracts project.
The author is essentially turning the compiler into the bad guy. It takes all the emotional weight out of architectural enforcement.
Yes, no more arguing in PRs. But you might wonder, though, how you test these concrete classes if they are completely hidden from the rest of the world. Because your unit test project needs to be able to instantiate the user service to verify its logic.
That's true. There has to be an escape hatch for testing, otherwise the whole system falls apart.
There is a highly specific escape hatch built into .NET for this exact scenario. It's an assembly-level attribute called internals visible to.
Oh, I've seen that.
Yeah. You place this attribute in your impl project, and it explicitly tells the compiler to keep everything hidden from the broader application, but to grant special exclusive access to your designated unit test project.
That's brilliant.
It perfectly preserves the architectural boundary while allowing for comprehensive testing.
That structural lockdown leads to the true realization of this entire approach. We aren't just hiding individual classes. We are enforcing the architecture at the project file level.
Right. What's fascinating here is looking back at the dashboard.impl project.
Let's do it.
It requires the iUser service and the iCurrency service to function. If you open the actual .cs proj file for the dashboard, the XML file that defines the project's dependencies, it only lists references to the contracts projects for user and currency.
So there is absolutely no project reference to gav.user.impl.
None. That absence of a reference is the most critical detail in the article. It means the boundary between the dashboard implementation and the user implementation is not just a convention.
Because a convention is just a polite suggestion written in a wiki somewhere.
Exactly. A convention requires human discipline every single day. It requires a senior developer to spot the violation in a pull request and start an argument about architecture.
And eventually, someone gets tired of arguing, the pull request gets approved, and the boundary is breached.
Yep.
But with this setup, the boundary is physical. It is enforced by the compiler. You cannot instantiate the concrete class because the project itself fundamentally cannot see it.
A boundary requires discipline exactly once when you set up the project structure. From that point on, the machine enforces the rules for you.
The author has basically created a compiler-enforced modular monolith.
Yeah. The project structure and the compiler act as unyielding architectural guardrails.
This does bring up a massive logistical puzzle, though. Yeah. If all of these implementation projects are completely locked down behind internal keywords and they don't reference each other, how does the application actually run?
Ah, the wiring problem.
Right. At some point, the interfaces requested by the dashboard have to be matched up with the concrete classes hidden inside the user and currency projects. Who does the matching?
That responsibility falls to the very top of the architecture, the host.
Meaning program.cs.
Exactly.
Okay.
In a modern .NET application, this is typically your program.cs file. The host project is the single piece of the entire system that is permitted to see everything. It sits above the fray and references all of the contracts projects and all of the impl projects.
But wait, if the concrete classes inside those impl projects are marked internal, how can the host project see them to wire them up? The VIP room is still hidden, even from the host.
The author handles this restriction elegantly. Every impl project exposes exactly one public class to the outside world. It's usually a static registration extensions class.
Just one public class.
Just one. And this class contains methods designed specifically to register that features internal services with the application's dependency injection container and to map any HTTP endpoints related to that feature.
Okay, so the user.improject exposes a single public method called something like add user feature.
Precisely. And because that add user feature method lives physically inside the user assembly, it has full access to all the hidden internal classes.
Oh, I get it.
Yeah, inside that method, it tells the dependency injection container, hey, whenever any part of this application asks for an iUser service, instantiate and provide this internal user service class.
Wow. So the host program.cs file becomes incredibly clean. It's essentially just a list of feature registrations, add user feature, add currency feature, add dashboard feature.
Yep. The host orchestrates the composition of the entire application without ever needing to know the names of the concrete types doing the work.
That's amazing. At runtime, the built-in dependency injection container just takes over.
Exactly. When the dashboard service is instantiated, the container sees that it requires an iUser service and seamlessly injects the hidden concrete class. The host knows about the feature boundaries precisely so that nothing else in the application has to. It is a masterful separation of concerns.
You know, beyond the mechanical beauty of the code, the author points out a cultural benefit to this structure that might be even more impactful than the compiler enforcement.
Oh, the folder philosophy.
Yes, the philosophy of the folder. When you strictly isolate features like this, the physical folder on your hard drive, for example, source feature user, transforms into the absolute source of truth for that entire domain.
It ceases to be just a container for C# files. It becomes the home for everything related to that business capability.
Everything.
Yeah, you can put the architecture diagrams for the user feature directly in that folder. You can include a readm file that explains the complex domain rules for user states. You can store the ADRs, the architecture decision records, right alongside the code.
Which completely solves our archaeology problem.
Right.
I mean, ADRs are so vital because context rots over time. When a new developer wants to know why a specific caching strategy was chosen for the user feature back in 2024, they don't have to hunt down a former employee or search through some external wiki. The decision record is sitting right next to the implementation.
You can even place a code owner's file inside that specific folder. Think about the friction of onboarding a new teammate. In the old layered black hole architecture, onboarding meant telling a new hire to grep the entire massive solution to try and trace how a user is saved to the database.
It's a psychologically overwhelming experience. It breeds imposter syndrome immediately.
Totally. But with the modular monolith approach, onboarding shrinks from search the whole solution to read this one folder. Everything they need to understand that feature is contained within those boundaries.
And with that code owner's file, ownership finally has a physical address again. It's no longer a case of everyone owns it, therefore no one owns it.
Yeah.
You know exactly which team or which specific developer is responsible for the health of the user feature.
Now, whenever you discuss architectural boundaries and domain separation like this, it's inevitable that someone will bring up clean architecture or hexagonal architecture.
Or for sure, it's the standard pushback in any design review. Why are we doing this instead of just using clean architecture?
The industry does love its architectural buzzwords.
So how does the author reconcile this feature-sliced approach with those established patterns? Like, do we have to pick a side?
Not at all. The author makes a crucial distinction here. These concepts do not compete, they compose.
Compose, okay.
Right. Clean architecture and hexagonal architecture are exceptional patterns for organizing the inside of a complex module. They dictate how to structure your domain logic so it remains independent of your database or your user interface.
But this compiler-enforced modular monolith approach is solving a different problem. It's about handling the boundaries between the modules themselves.
Exactly. The contracts project acts essentially as the port in a hexagonal architecture, applied strictly on a per-feature basis. If the internal business logic of your user impl project becomes incredibly complex, you are entirely free to implement clean architecture inside that specific project. The external boundary, the compiler guardrail we set up, does not care what architecture you use inside the VIP room, as long as you continue to honor the public contract at the door.
I love that. It gives you the flexibility to let simple features remain simple, maybe just a basic C or node operation, while allowing highly complex features to adopt rigorous internal architectures. And you do it without that complexity polluting the rest of the application.
That highly cohesive, loosely coupled state is basically the holy grail of software design.
So what does this all mean? Let's trace the arc of what the author has laid out for us today. We started with the trap of the common library, that junk drawer that inevitably turns into a black hole, sucking in dependencies, destroying clear ownership, and turning the dependency graph into an unnavigable hairball.
And we recognize that horizontal layers only exacerbate the problem by smearing a single business feature across multiple technical projects.
So the way out is to slice the application vertically, organizing by business feature to create one folder, one boundary, and one owner.
And to prevent those vertical slices from tangling together, we divide each feature into two distinct parts. The contracts project, containing only interfaces and acting as the public API, and the implementation project, where the concrete logic is hidden away using the internal sealed access modifiers.
And the crowning achievement of this architecture is that we do not rely on human discipline to maintain it.
No, we don't.
We use the project references in the .cs profile and the unyielding rules of the compiler to enforce those boundaries. The features communicate strictly through interfaces, and the host project wires everything together at runtime using the dependency injection container.
It represents a significant paradigm shift. I mean, it does require an initial investment of discipline to set up the infrastructure. You're creating two projects per feature instead of one, and you have to be very deliberate about your interfaces. But the ongoing maintenance cost drops dramatically.
Because the machine is doing the heavy lifting for you. You don't have to waste time arguing about dependency rules and pull requests, because the compiler physically will not allow a developer to break the rules. It is a system actively designed to keep your code base healthy and comprehensible as it scales over years, instead of slowly deteriorating into a massive big ball of mud.
You know, as we wrap up, I want to leave you with a final thought to mull over, drawn directly from the author's closing reflections.
Okay, let's hear it.
The author is pragmatic. They acknowledge that this architecture is a powerful baseline, not an unbreakable dogma. Stepping away from it to solve a unique technical challenge is perfectly fine, provided you carefully estimate the risk and the technical debt you're taking on.
Makes sense.
But consider the alternative. If you choose to step away from this discipline, if you bypass the compiler's strict guardrails simply because it feels faster to throw a helper method into a shared folder on a Tuesday afternoon, aren't you just, quietly planting the seed for a brand new black hole?
And before you know it, you will find yourself right back at that junk drawer, digging through the dried up superglue and the dead batteries, desperately trying to find the scissors. Thanks for joining us on our discussion today. We will see you next time.